Hi, I'm Sophie Earhart,
And I'm Kit Carney.
and this is our physics vehicle analysis video.
Hope you enjoy!
The problem we were given was to design a vehicle that is able to propel itself using only mechanical energy to go about 45 feet.
Our hypothesis was that by constructing a wooden structure with heavy wheels that was propelled by wrapping a rubber tube around one of the wooden structure's axles, the elastic potential energy that was present in stretching the string would provide enough force to drive the vehicle about 45 feet.
For our design, we built a rectangle frame using pieces of wood attached at right angles. We had two different sizes of wheels, big in the back and small in the front. Our back axle is metal because it had to withstand the force of the rubber band stretching. The front axle is also made of metal because it let the wheels turn more freely. We measured and drilled holes through the wood so that the axles were exactly straight. We also attached a hook to the front of the vehicle because it allowed us to stretch the bands further, so we had more elastic potential energy stored. This is a picture of our final design. The following trials are the processes we went through in obtaining our final design. In creating this vehicle, we had many trials, all of which utilized the wooden structure and wheels that we had built. In one trial, we used part of a swimming noodle and placed this along the axle around which we stretched the rubber tubing. This did not propel the vehicle far enough because the increased distance that the noodle created for the axle created less force upon the axle, and this small force was not enough to propel the vehicle far enough. This relationship between the force and the distance is related to torque, which we will discuss later.
In another trial, we used TheraBands instead of the rubber tubing. However, the stretching of these bands did not result in the right amount of elastic potential energy that could be transformed into linear and rotational kinetic energy, which meant that our vehicle was still not traveling the proper distance. In a final trial, we returned to the rubber tubing and replaced the wooden axles that we had been using with metal axles, because the wooden axles were having trouble withstanding the amount of force that the rubber tube was exerting upon them. In this trial, we had not yet replaced the axles, and the vehicle barely moved. After we replaced these axles, we were able to stretch the rubber band much further, and we were able to store much more elastic potential energy. And this amount of energy allowed for the vehicle to travel the desired distance. When we were doing these trials, we had to take into account all the forces acting on our vehicle. Normal force, the force that acts on a surface in a direction perpendicular to the ground, that is applied by the floor, was acting on its vehicle.
The gravitational force, which is the force of attraction between the vehicle and the earth, is also acting on the vehicle.
Also acting on our vehicle was centripetal force, the center-directed force keeping an object in circular motion. It was acting on the wheels and the axles, and the rubber band while it was wrapped around the axle of the vehicle.
Frictional force, the force that acts between objects in contact with each other, that opposes motion or impending motion between the objects, is present in aspects of our design. A frictional force acts against the axles as they spin in the frame of the vehicle. A static frictional force exists between the vehicle and the ground and acts in the direction of the wheels. The wheels are moving as the vehicle is accelerating. When the wheels are decelerating, the static frictional forces opposes the motion of the wheels.
We also had to consider the coefficient of friction. The coefficient of friction is the ratio of the frictional force value to the normal force value acting between two surfaces. This was most important in considering which materials we should use for the axles of the frame. At first, we used the wooden axles with a wooden frame, but then we found that metal and wood would have a lower coefficient of friction so that the wheels turned more easily. We also had to consider torque. Torque, the quantity you apply to an object to change the object's rotational motion, was important in figuring out the right size for the axles. A smaller axle would mean that the force is applied closer to the pivot, so more force is needed, but you also get more revolutions and travel farther with the same amount of force applied further from the pivot.
In one trial, we used part of a swimming noodle around the axis. However, this increased the diameter of the axle, so the force was applied farther from the pivot, and though less force was needed, The vehicle did not travel as far because there were fewer revolutions of the wheels. Linear motion. Inertia, the tendency of an object to resist a change in speed or direction, was another factor we had to take into consideration. Our vehicle had a large mass, so it had a lot of inertia. This means that we needed more force to get the vehicle moving because it wanted to stay at rest, but also that once the vehicle was moving, it kept rolling even after the rubber band wasn't propelling it anymore.
Acceleration, the rate at which the velocity changes over time, was important in this project. For this project, the vehicle had to start from rest, accelerate using mechanical energy, travel a certain distance, and then decelerate to a stop at the right time at the right distance.
We did not attach the rubber band to the axle because we wanted the distance and displacement to be the same. If the rubber band was attached, the vehicle would have moved forward and then moved backwards again, so that though it may have traveled the right distance, the displacement would have been less.
According to Newton's second law, when a net external force is applied to an object, it causes the object to accelerate in the direction of the force. In the case of our vehicle, the force applied is rotational because the rubber band unwinding is what is causing the motion. As the rubber band unwinds in a rotational manner, it causes the axle, and therefore the wheels, to rotate, which is how our vehicle moves. This rotation creates a centripetal acceleration.
Centripetal acceleration is the center-directed acceleration of an object in circular motion. In our case, the wheels and the axle, which act as a single unit because they were glued together, experience centripetal acceleration. The centripetal acceleration of the wheels causes a rotational acceleration, which translates to a linear acceleration of the vehicle.
Lastly, we need to talk about energies. Mechanical energy is any energy associated with an object due to the object's position or state of motion. For the project, we were instructed to construct a vehicle propelled only by mechanical energy.
Potential energy is the energy associated with an object due to the object's position. Our vehicle had no potential energy as it sat at the beginning of the hallway before we winded the rubber band. However, as we winded the rubber band, elastic potential energy was present.
Elastic potential energy is the energy associated with the stretched or compressed elastic substance. Our elastic substance was the rubber band. As we stretched the rubber band and wound it around the back axle of the vehicle, we created a great deal of elastic potential energy. When we released the rubber band, this potential energy began to be converted into kinetic energy as the vehicle accelerated forward. Some energy was lost as heat and sound.
In deciding which elastic substance to use, we had to consider the spring constant, the force needed to stretch an elastic substance 1 meter. We wanted a medium-high spring constant because we didn't want it to be too hard to stretch the substance, but it had to be difficult enough to stretch that it would cause the vehicle to accelerate forward.
Kinetic energy is the energy associated with an object due to its state of motion. Kinetic energy was present as the vehicle moved from the starting point to the finish. Now that we've talked about the conceptual parts of our project, now we need to talk about how it performed. For our results, after many trials, we determined that discarding the swimming noodle, TheraBands, and wooden axles, and adding rubber tubing and metal axles, that we were able to get the vehicle to travel the desired distance.
Our vehicle was designed well enough that it was able to reach into the master shuffler zone, which was our goal for this project. Our utilization of medical tubing provided the elasticity that was needed to propel our heavy vehicle, which had a great deal of inertia, about 45 feet.
The following video is the final trial that we did right before we actually performed the physics project. It was actually the day before, and it was successful and it went into the right distance, so we hope this would be kind of similar to how it was an actual testing day. So hope you like it, because it worked. This has been Kit Carney
And Sophie Earhart.
Hope Hope you enjoy pondering our video.
That's good. Oh wait, it's gone.
According to Newton's second law, when a net external force